We're going to take a closer look at fission reactions now. Fission reactions are decay reactions because they involve unstable nuclei turning into more stable nuclei by emitting energy somehow. We don't call them radioactive decays though, because they don't emit alpha, beta, gamma or positron, but they are decays. There aren't very many things that decay by fission, but this is one of them. So this is plutonium-240. And it can decay by fission into these things here. So what's going on? You have in fission a large unstable nucleus that falls apart into two smaller nuclei and some leftover neutrons. Now I know that these three neutrons are separate because if they were stuck together, the three would be there. And there'd be a different symbol instead of the N. So these are definitely three separate neutrons. And this is important for what's going on with the energy. This reaction is exothermic, it gives out energy. Now, in reality, some of that energy is coming out as gamma radiation, but we sort of ignore that for your A level. Notice we haven't put any photons on the end there, so we're ignoring that. Instead, we're saying that all the energy comes out as the kinetic energy of these neutrons. So you have to imagine big nucleus falls apart into two smaller nuclei, and then these three very energetic neutrons fly out, and it's their kinetic energy that came from this reaction, that was released in this reaction. Okay, before we do a practice question, we're just going to note that you can't dig up plutonium-240. You have to make it, and we make it from plutonium-239, which you also can't dig up. This one is a byproduct of nuclear reactors. That's where you get that one from. But anyway, however you get it, there it is, and we obviously need to make it take in a neutron. To do that, we're going to fire neutrons at it, but if these neutrons are moving too quickly, they'll just bounce off. So they need to be moving relatively slowly so that they can actually be taken in. They can react with the nucleus and be taken in by the nucleus and form plutonium-240. And we've got a special name for these slow-moving neutrons. We call them thermal neutrons. Okay, so here's a lovely big question now, which pulls that in also with all of the binding energy stuff. And for the first part, you can either say that the total mass before is bigger than the total mass after for the first mark, and for the second mark, the missing mass has been turned into energy according to that formula. Or you can say that the total binding energy after is bigger than the total binding energy before, and for the second mark, the change in energy is the energy that's released. Next part, the energy is released as the kinetic energy of the neutrons, and explain why the neutron is not in the table. Nice question, this one. The table shows binding energies per nucleon. Remember that binding energy is the energy required to pull a nucleus apart into its constituent protons and neutrons. Now, that means that neutrons have no binding energy. You can't pull a neutron apart into its constituent protons and neutrons, or in any sense in which that you can do it, it would be zero. So that's why it's not in the table. And lastly, our big energy calculation there. So the energy released is going to be the total binding energy after minus the total before. The total before is this. Remember, this is the binding energy per nucleon, so don't forget to multiply by the number of nucleons there. And also notice that the neutrons don't feature. As we said in the previous part of the question, the neutron doesn't have any binding energy. So there's the total binding energy before, and then we're taking away the total binding energy after, and that gives us 185 MeV.